Alright, hello everyone. Today we're going to add our fourth tutorial, and we're going to begin with naive Bayes classification. So the idea today and over the next couple of tutorials after midterm week and reading week is I'm going to go over various classification techniques, and the idea that I want to give to you guys is the intuition on what each of the techniques does and how the classification is done. So eventually when we learn how to do cross-validation, model evaluation, and parameter tuning, you get a better sense for which algorithm to use. So in class you're going to learn multiple classification techniques. So you've just learned naive Bayes and decision trees, but eventually you'll learn support vector machines and logistic regression and another series of algorithms. So the goal of today's and next week's, not next week, but when we start tutorials again, is I'm just going to go over multiple algorithms, visualize them so you can see how the decisions are made, and then give you standalone code that which we can use. So in the first bit of this tutorial, I'm going to begin with made up data and show you naive Bayes on 3 sets of data that I made up, and then I'm going to eventually use naive Bayes on the iris data set that we looked at previously, and I'm also going to show you a really powerful example of naive Bayes with text data. And then I'm going to do the same thing with decision trees. And later on, if we have time, we'll go into more advanced topics for decision trees. So as we learned in the notes, naive Bayes works on the Bayes theorem. So the idea is it uses this formula where we take the probability of A times the probability of B when A is observed, divided by the probability of B is the probability of A when B is observed. And as Professor Golab went over, you can apply this to classification by taking the probability of a class by observing the features is equal to the probability of the features when observing the class multiplied by the probability of the class and the probability of the features. And Professor Golab also did go over how you can go into numeric, and the example is here, where you can actually get the mean and standard deviation and be able to do a numeric example. And the nice part about Python is the naive Bayes algorithm is already implemented. So if you do from scikit-learn.naive Bayes, they have different versions of naive Bayes, and this is just the Gaussian version. But if you search naive Bayes scikit-learn, you can actually read the documentation, and it also goes a little bit into the theory, but it goes into the different types of naive Bayes. So for today, I'm just going to show the Gaussian, which is what Professor Golab went over. But there's additional naive Bayes algorithms that you can use as well. And the point of me showing you this code is eventually you should be able to change from Gaussian to any other ones, and you can use the same code that I provide to get an intuition on what that algorithm will look like, whether it's naive Bayes or whether it's any classification technique. So right now what I'm going to do is I'm going to make classification data, and there's actually a function in scikit-learn called make classification, and it's in the datasets, so you can make different types of data. So in this example, I'm just going to make dummy data to show you an intuition of how the algorithms work. I'm going to go into making moons, making circles, and then making a classification, which is just going to be linear. So basically, in this code, all I'm doing is I'm making 3 sets of data, one of them being moons, one of them being circles, and the other being linear. And if we run this code, okay. So we can see each of the data sets, and the reason that it's popping out is because I don't have matplotlib inline. That's better. Okay, sorry. So we used again matplotlib inline to make the images appear in the browser in Jupyter Notebook. So here are the 3 data sets that we're going to be working with today. This is make crescents, so we can see that the data has interlocking crescents. This is just again dummy data that I just made up. Again, so So it's 2 features, and then the color is the class. So we're just going to call it blue and red for now, but this could be anything. It could be male, female, it could be whatever you want. So I'm just trying to show you the intuition of what happens when you apply an algorithm to a data set that is separable. It's not very separable because it's created crescents. And this example is make circles. So we can see in the center we have about a blue circle, and then around the outside we have red. So if we were to classify it, if you wanted to split this data, you might want to use a circle. In this case, you might want to use some form of a crescent, or it's pretty difficult to be able to do. And the last one is this is pretty linearly separable. So maybe if we draw a line down this way, we can separate it. So what I'm going to do is I'm going to show you how you can use naive Bayes to be able to do it. This example also, if you notice the colors. So again, I split my data into training and testing data. And the one way to do it, not the very best way, is to do train test split. So by using train test split, I give it my x, I give it my y, where y is your classes and x are your features. And then I say test side is 0.4 or 40%. So we test on 40%, we train on 60. And you can change this number to whatever you want. Generally, it's 70% that you train upon and 30 that you test. In the next couple of lectures, you're going to learn how to actually do cross-validation and how to do k-folds. So for now, I'm just going to show you this, where you split into 40%, but eventually we'll go into doing it a better way. But for now, if you notice, the dark red dots are training data, and on our light red dots are our testing data. So the data set's split. So again, we're going to train on some of the data, and then when we test, we're going to test on it on a different set. And I'm also going to go into model evaluation, which is how do you tell whether classification is good or not, and we'll go into that very shortly. So now what we're going to do is for each data set, we're going to again split it into testing and training. So I'm just rerunning the same code. So this example is mostly for illustration purposes. You probably wouldn't need to use a lot of these things that I have. It's just to make it look nicer. The visualizations look nicer. But so here I'm basically using the classification that I used here. So we're using Gaussian naive Bayes. And for each classification technique, what I'm going to do is I'm going to actually predict using the classifier. So I'm going to fit. So by doing clf.fit, I'm using the classifier to fit based off the training and the training data. And then score is equal to classifier.score x test, y test. So I just want to go over model evaluation very quickly. So when you do regression, you can model how good your algorithm is by using, for example, the mean sum of squares error, or the MSCI. There are other metrics that you can use. For classification, there's a whole set of other metrics that you can use. So if we search model evaluation scikit-learn, you can actually read different scores that you could use. So for one of them, for example, is accuracy. You can use precision. You can use F1 for binary. You can use ROC AUC, which I'll show you very shortly. And for regression, you can again use like the mean absolute error, the mean squared error, or the R2, where the R2 is the coefficient of determination. So that's if you're doing regression. There are all these different metrics you could use, and really what matters is understanding what is very important to you. So very shortly, Professor Golab will go over confusion matrices and trying to understand what false positives are, what false negatives are. And then basically there's a trade-off. So depending on the scoring methodology that you use, there's a trade-off. Usually when you just use the standard score, it will just use accuracy, but accuracy is not always a good measure. And maybe in a future example, I'll show you where that's bad. But for example, in a project that I was doing document classification, so identifying what a document is about. And what I found when I used accuracy was there was one class that had very few documents. So my classifier to get the highest accuracy would say none of the documents is about this. So I would get really high accuracy, like 98% accuracy, but that's only because 2% of the documents were about that topic. So it wasn't that useful because my classification just said everything is everything is not about that document, and it got 98% accuracy. So depending what you're using, there are a large number of other metrics. If you want to read more upon it, you can actually look at the Wikipedia article is actually pretty good. It explains, it can explain, precision and recall and confusion matrices, and it'll teach you kind of what the true positive rate, specificity, the F1 score, the Matthews correlation coefficient. This is if you have binary. It's very good, and it's evened out. So it's a balanced measure that you can do if you're doing binary classification. But there's also other types of scores, and kind of understanding the metric to use is very important. So in this case, I'm just showing you a very simple example using the standard score, which will just be the accuracy, and we'll see what that looks like. So I just wanted to let you know that there are different types of scoring that you can use, and by reading the documentation you can get a better sense for it. So in this case, what I'm doing is I'm also going to put in the colors, which I'll show you very shortly. So if we run the code, this is how naive Bayes classified our data. So if you look at it, the great part about naive Bayes is that it gives you a probabilistic estimate as well. So it not only tells you the class, but it tells you the probability that it is of this class. And this is what the shades of red look like. So the dark red is where it split the data. So it says with a very high probability, any point behind this line is probably a part of the red class. And then as we go down, it becomes lighter and lighter, and then it goes darker and darker towards blue. And I also put the accuracy score here. So this algorithm is about 90% accurate in this example only. And that kind of makes sense. We can see quite a few of the blue dots on the red side of the line. So we can see that it didn't really get those moon shape out of it. But it worked pretty well. It gave us a pretty good accuracy, and it split the data pretty well. And again, this is just intuition on these data sets. When you deal with your data sets in your project or in the real world, the algorithm might not always perform the exact same way, but it's important to try and understand in the beginning kind of how it works. And the main assumption, again, that we're making is that they're independent. So we have to have the independent assumption when we're using naive Bayes. If we go down to the circle data, we can see here that it worked, the naive method worked actually quite a lot better. So we can see in the center that we have the blue class, and as we move out, it determines the class as well pretty well. And again, if you look at the score, you might think, oh, 85 is a bit low. But what you need to remember is that, again, we're doing it based off training and testing. So if I choose a different sample size or I shuffle the data before, this accuracy score will be different because we're trying it for a random set of test data. And that's the real hard part about determining the best classifier is that there's no correct answer. It all depends on your data set. So there is no optimization technique you can use that will guarantee you the best answer, and there's no one algorithm that's the very best, and that's the no free lunch theorem. So later on, we're going to learn how to do model evaluation and parameter tuning to try and get better models, but we're never guaranteed we have the best. So again, this is for circular data, and then this is somewhat linear separable, but there is kind of an arc, and we can see here as well that that naive Bayes works pretty well in splitting the data from left to right. So the next thing I want to go over, so hopefully this gives you some intuition. The goal is over the next couple of tutorials, I'm going to start adding other algorithms so you can see, and you can compare each one against each other in these 3 data sets which I made up. So hopefully that gives you some intuition. So let's move on to the iris data set that we talked about. Whoops. So if we go back to the iris data set, which we talked about, again, there are 3 types of flowers, and we look at the petal length, petal width, sepal length, sepal width, and we're trying to classify the data. So just to remind you guys, in our exploratory data analysis tutorial, we went over the iris data set, which is over here. So here we can see the sepal length, sepal width, petal width, and we can see the three types of iris: iris centosa, iris versicolor, and iris virginica. And the goal here is, given these sets of data, to split them up and to do classification. So we're dealing here with a multi-class problem. So there are 3 different classes, and we have basically 4 features. And based off of this data, we want to try and split up. So if we get a new flower and we take these measurements, we can predict or classify what type of flower it is based off their characteristics without having to look at the flower. And that's really like a good classification problem. So if we go back to the naive Bayes, basically this is a very, very simple example. I'm not using cross-validation here, so you should always use cross-validation. The reason that I'm not using cross-validation is because I want to show the intuition on where we might be overtraining or not. So I'm going to do it without cross-validation, just so that we can kind of get a sense for which algorithms might be overtraining, which are prone to or not. And then in the future, when you learn cross-validation, you should start using it. So basically, you can also load datasets. So the iris dataset, instead of opening it through the CSV, you can also just load it. And again, we're going to use a Gaussian naive Bayes, and we're going to fit the data. So normally you would split it into test and train, but I'm just going to fit it on the raw data. I'm going to print the model, and then I'm going to so the expected is our target. So when you load the data set, this is your y, and then the predicted is your y hat, or based off the x data, which is the data set data, we're going to predict which class it's going to be, and that's predicted. And then what I'm going to do is I'm going to use two metric functions that comes with Python. So all of those metrics which I talked about, precision, recall, F1 score, you can actually see them down here, but that was just done by doing classification report. So if you read the metrics documentation, you can actually read kind of how this works. So it's a lot easier than having to manually write code to get your precision, your recall, or your accuracy, as well as your confusion matrix. So if we run this code, we can get the result down here. So here we can see for each of the classes, so this is class 0, class 1, class 2, and that's based off the data set. So those are the 3 types of flowers. We can see the precision, recall, and the scores, and then we can see the average. And we can also take a look at the confusion matrix. So in class, you're going to learn what the confusion matrix means, but in short, each one of these columns represents 0, 1, and 2. So, and then this is 0, 1, and 2. So you have your predicted versus your actual. And down the columns are the ones that you're right, and then the ones on each row that are not on the diagonal are the ones where you incorrectly classified one where it was supposed to be another. So Professor Golab will go over this. I just wanted to give you the code such that you can create your own confusion matrices and be able to analyze it on your own. But these are just some metrics that you can use, and you can see that across each of them the scores are pretty good. Just very quickly, I wanted to go over text classification and a good use case for naive Bayes. So the real power with naive Bayes is its simplicity and its speed. So one thing that you can do, because you can set your own set of features when you're using text data, and let's say you want to classify text data, like an email, you want to classify if the email is important or not, or if you're classifying like a book, what the book is about, or something like that. There's a lot of features you can have because you just have a full text. So in this example, I'm going to take a bunch of news groups, so just emails, think about them like emails, and we're going to classify them what topic they're about. They could be, and these are just sampled categories that were in the data set. It could be about atheism, religion, graphics, or space. Computer graphics or science and space. And these are just basically a 4-class problem. So the way that we can represent our data is we can do it based off the term frequency. So for example, you can get the computer or Python to look at all of the text, tokenize the text, so break them into either individual words or 2 words or 3 words, like tuples, and then get the frequency of each of them. So for example, in this in this example, you can see beginning has 1, Earth has 2, God has 3, just for example. Another thing you can do is you can look at the inverse document frequency. So look at the frequency of each of these words across all the documents. So if the documents are very frequent in a text, but they're not frequent across all the words. So for example, God, if you take a lot of text, that God will be very frequent in religious texts and will also be very infrequent in other texts. So that therefore you can use naive Bayes on seeing the word God in all of the text, determine whether the text is about religion or not, using God as a feature. Or you can use earth, or you can use beginning, or you can use all of this set of words. And this is called a bag of words technique. It's a very simple, very easy way you can use document classification, and I've used it just as a benchmark. I just quickly split up the text using a vectorizer, and then was able to do it. So there is a special package in Python called NLTK, or the Natural Language Toolkit, which has very powerful things that you can use. So I'll just open that up really quick. So I don't know if any of you guys are doing natural language processing, but it also has a book. And if you look at the NLTK book, it kind of gives you sample code on how to tokenize and get inverse document frequency. And if you go through some of these examples, you can actually deal with text data. So I'm not going to go too much into detail about it, mostly because I don't think everyone's doing it. But I just wanted to show one example. I'm just going to explain the code very quickly. So it basically gets a bunch of emails, and it tries to determine what the categories of the emails are. So if you actually go to data train, if we just take a look at our data set, so whoops, we do insert cell below. If you actually just take a look at our data set, it might take a little bit to open, but it's just a lot of text data. Like this is the data. It's literally like emails. There's some email addresses with names, and there's just a lot of text. And processing this can be very, very difficult, right? Because there's tons and tons of words. What you can do is use naive Bayes, and it runs in a couple of seconds. So basically, we take our data set and we split it, and we also shuffle it as usual. We get our categories based off the names, and then we use a vectorizer. So in this case, I'm using a hashing vectorizer. And what I'm doing is I'm going to use English stop words, meaning common words in English, such as of or the or a or an, or all these words that add noise to our data set are removed. And that's what stop words are. And then in this case, I use 1,000 features, or 1,000 words. So it's going to use only 1,000 words to be able to do it, to run it quicker. So this number we can change, and this vectorizer we can use. This is just a hashing vectorizer, but you can also do the term frequency, inverse document frequency, or you can vectorize based off of different methods. So you can get tuples, and then basically what it does is it uses two versions of the naive Bayes. One is the multinomial, and the other is Bernoulli. So in the previous example, I used Gaussian, which is the basic one that we learned in class. You can also use other types of naive Bayes that Python has implemented, and you can read the documentation for how each of these works. And basically, for each one, I essentially fit the data, and then I also test. So I also try and get the false positive rate and the true positive rate. And then here I do a ROC drawing, or sorry, an ROC, graphic. And what that shows is the true positive rate versus the false positive rate. And that's very useful if you're doing classification. So if you Google search ROC, which is the receiving operating characteristic, it kind of explains what the ROC curve means. The goal of the ROC curve is you want it to have as high of a true positive rate as possible and have as low as a false positive rate as possible. So you want the line to go straight up and to the left. And what you can do is you can take the area under the curve, and as close to 1 means your classification is better according to this metric, which is the true positive rate versus the false positive rate, which means you're trying to optimize to get the most amount of true positives compared to false positives. So again, I'm just showing you this example if you're going to use it in your project. The true positive, false positive rates, and this stuff will make a lot more sense when the professor goes over cross-validation and on your valuation metrics. I just wanted to show it to you now. So if you do see sample code on the internet that you're using for your projects, it'll make a lot more sense. So basically, this is just a metric. And by looking at the graph, I can visually inspect which one is better in this case. So for example, multinomial naive Bayes is better according to the ROC. And I could also get the area. And again, ROC and those are also in the model evaluation. So in the model evaluation, you can calculate the ROC AUC. I guess it has its own section, and you can also calculate it using the ROC AUC, which computes the area under the curve. And then you just give it the true, and then the one that you predicted, and then it will actually just calculate it for you, and it will return you the number, the float between 0 and 1, which represents how good your classification is. So you can use that as a scoring metric, and here's an example of it. So in this case, with this like sample data that they just had, it has about 0.75 AUC ROC. And you can also build it using Python as well. And if you actually click that example, it will show you how to make the ROC, and then it uses it with, I guess, different types of classes. So that's one metric that you can use. So what I'm going to do now is I'm going to do a similar techniques, but I'm going to apply it using decision trees, and then I'm also going to go into very common classifiers that build upon decision trees, such as random forest and Adaboost and also extra trees. So again, in class you learned how to do entropy-based decision trees. So the way that works is it calculates the entropy and then it makes decisions off of the entropy. And I'm going to show you an example of that. But what you can later do is build smaller decision trees and ensemble them together. And we'll learn a little bit about ensembling, a little bit about boosting. But first, let's try and get a visualization for how decision trees work compared to naive Bayes. So again, I'm using the same code that I used last time, and I'm adding decision trees, and I'm adding naive Bayes. So we can see them kind of side by side, again, for the same 3 data sets that I just made up. So if we run this code, this is kind of what we get in terms of the classification. So again, here this is our naive Bayes. We split it. We split the crescents this way. With decision trees, we can see it actually was able to pick up the crescent shape a little bit better based off of the entropy-based decision trees that we talked about, and it also has a higher score compared to naive Bayes again, and that's using cross-validation. On this side, we can see with the circular data, the decision trees actually made the decisions slightly differently. It split the data based off of squares instead of circles, and that's just, I guess, the way that the algorithm worked based off the entropy. But a very interesting point we can see here is you can see this line, this like sliver of red, which means it's just picking up these red dots. And really what this kind of shows us is that we might be overfitting, because even in this example, we can see that sliver of blue that's picking up that one blue point. So for example, if there's a red point that's here, most probably, if there's a new point here, most probably it would be red. But if it's in that line that I showed you, it's actually going to predict it as blue. Same over here. We might have a blue point over here or down here that actually would better be represented as blue according to naive Bayes, but it'll be predicted as red. So just the intuition is that we might be slightly overfitting using decision trees, or at least decision trees are prone to overfit. So that's kind of a disadvantage, and compared to with naive Bayes. But with naive Bayes, we're making that assumption of independence, which might not also be true. So again, there's a trade-off for which algorithm you'd want to use. Now if we look at the linearly separable data, we can see here that it split it pretty well, almost down the middle, compared to the arcs here. So again, there's no right answer. There's no which algorithm is better than the other. What matters is the way that it performs on real world data in the future, which you don't really know. So hopefully that gives you a little bit of intuition. So the next thing I'm going to do is I'm going to talk about two other decision tree algorithms. One is called random forest, and the other is called Adaboost. And random forest is very popularly used in industry, and people almost sometimes just blindly use random forest because it performs very well. And same with Adaboost. And the general concept behind these advanced types of decision trees or machine learning in general is it does a thing called ensembling and a thing called boosting. So another advantage of a decision tree, which we'll see soon, is we can actually plot out the decision tree and see what it looks like, which makes it actually very comprehensible by the layperson. Or you just look at a decision tree and understand how the data is being split. By using random forest and Adaboost, you are removing that comprehensibility, but and I'll show you how, you're increasing your performance. And the way that works is it builds a very weak tree. So it'll build a tree, and then it will build another tree, and it'll keep building multiple trees, and it will ensemble them together. So it'll turn multiple weak classifiers into a stronger classifier. And if you take signal processing, that's a very common technique to be able to do. Take multiple weak signals, and by putting weak signals together, you get a stronger signal. It's the same concept. And that's the idea of ensembling. It's a little bit outside of the scope of this class. I just wanted to present random forest because it's very popular. The other one is Adaboost, which uses boosting or bootstrapping. And what bootstrapping does is it subsamples the data. So it takes a smaller set of the data, builds a classifier, and then takes another small sample, builds a classifier, and combines these classifiers together. And if you read the documentation, random forest is very popular. So in many contests, like in many machine learning contests, people use ensemble methods because they are just very powerful. So mostly like Kaggle, which has data science competitions, a lot of people have won just in the past just using straight random forests. And you can kind of read what it does, but it fits a number of decision trees on subsamples of the data set and averages to improve. And I guess if you read the ensemble methods, it'll explain like all the different types. So there's bagging. It'll talk about random forest, so building multiple trees. And this is the example that I'm going to show very soon. And there's also, you can also search up Adaboost, and it goes over kind of how it works. So again, these are ensemble techniques. They're optional to use in your project, but they give you they generally give better performance for a loss comprehensibility of the model. And they also help prevent overfitting as well. Since decision trees are known to overfitting, there are multiple implementations. So there's one made in Java called C4.5, which is also popular. And then a lot of people just use random forests because they don't require much tuning. But one thing I wanted to talk about is the idea of tuning and what that means. So both with Adaboost and with random forest, you can see here that it takes in parameters. So in this example, there's n estimators, which is the number of estimators which boosting is terminated. So it tells you how many estimators you should use. If you look at random forest, again, it has a number of features. So how many features should we use? Should we use Entropy or should we use Ginny? How deep should we build our tree? And what are all of these are all various parameters you can use that will again help make your model better. And when I mean better, it will help you A, to try to prevent overfitting, and B, try to prevent underfitting. So again, we're facing a bias and variance trade-off. So we want to be able to pick good parameters that will help us generalize with real-world data. And eventually we'll learn how to tune these parameters. I just want to show that these parameters exist. In the sample code that I have here, I just use max depth 5 and 10 estimators and one feature. But again, you can use various numbers and you can evaluate how each of these perform to make your final decision. So for example, if you're building something for the stock market, or you're building something where you were getting a very high score with real world data is important, then you want to spend time to pick these parameters well. So again, if we just run this code, what we'll see is, I guess the figure is a little bit small, maybe I can zoom in. So this is just, I guess, how each of the algorithms work. So it's a little bit hard to see here, but decision trees, this is random forest, this is Adaboost, and again, this is naive Bayes. So again, we picked a different set of training and testing data, and we can actually see that the algorithm performed slightly differently. I wasn't able to pick up those curves again, but it worked. Kind of well. We can see here we might be overfitting again. When we use random forest, since it's ensembling and it's taking multiple weak estimators, we can also get a probabilistic estimate for how well we're doing. So just like naive Bayes, where we can get different shades of red, or how certain are we that it's a part of that class, we can do the same thing with random forest. And the great part about it here is we can see in this region, there aren't really any dots. We don't know how it's going to perform. Maybe with real world data, it's actually blue, and the algorithm detects that and is able to tell, hey, we don't have data here, we can't really make that great of a decision. But in the red areas, we can know that it's a part of the red class, for example. And we can see it kind of picks up that shape. And again, we can see pretty good performance. So in this case, we have almost 97% accuracy in this example set using random forest. So we can see that we can increase our performance a lot. But again, how that, there's many papers which explain how random forest is implemented, but you lose that comprehensibility of your model. You can't just break it into a simple decision tree because it's multiple decision trees put together. And here we can see again, with naive Bayes you get the circles. Here we again get the squares, but we see here that we are somewhat preventing that overfitting that we were talking about before. So there isn't these bands of blue and red in between. We just have less probability in certain areas. And again, that's with Adaboost. And then with the linear separable, you can see that it separates it as well and gives you highlights. And it has all different scores. So really, which algorithm in this case is the best? The answer to that is it depends. It truly depends on the type of data that you have. So this is just some intuition of decision trees and naive Bayes, which you can use in your projects. Again, let's do it on the iris data set. And this is a lot simpler code that you can just use straight away. So again, we can use a decision tree classifier. In this example, I'm going to use Entropy because that's what we learned in class. You can also use Ginny. If you write Ginny, it'll work as well. But let's just use Entropy in this case. We're going to fit our data. We can print the model, get the expected, the predicted, and then we can also get the metrics. So here we can see when we run this, we get almost perfect precision, recall, F1 score, and support. And again, I'm not using cross-validation, and that's why I wanted to show you that. Is here it's saying that it can perfectly predict the iris data set just using decision trees. And usually when you get a very, very high score, like if you see like 100% or 1, you generally know you're probably overfitting. Most probably you're overfitting. But you can see here that decision trees sometimes are very prone to overfitting. The other thing you can do is you can actually visualize what that decision tree looks like. And you can export a tree using export graphic viz into a dot file. So dot is it's a type of file that basically draws trees and graphs. And if we go to the tutorials, we can see here that it creates this iris.dot file. So if we open up the iris.dot file, we can see here what it'll do is it'll actually just code which helps generate that tree file. So it'll show you the entropy and samples, and this isn't very visible. I just want to show you what it generates. And then using that dot file, what you can do is you can actually make a PDF or an image, and it will actually make out the. So this is a little bit hard to see. I'm just going to open it in a different PDF viewer. It's again a little bit hard to see because of the resolution. But anyways, so what it does is in the beginning, you have all three of your classes, and it calculates the entropy. And then it makes a decision and says, if x3, so for example, I think that is sepal length, or if one of the features is less than 0.8, and that's true, then we know that it's of this class. If not, then we use the other one, and we pick again based off the entropy, and we keep iterating through, and then at the end it goes down to in this example entropy 0 for each of them. So that's why that's why you might think that it's overfitting, because it's basically picking the ones with 0 entropy. But again, it's very similar to what you learned how to do in class, but it does it for you. It calculates the entropy for you instead of manually. And here it shows you the number of in each class and how it splits it up. And again, this is true and false. And this is just an example of visualizing what that decision tree will look like. So that's how you use decision trees. Again, you are prone to overfitting. So eventually, when you learn how to do cross-validation, you should use cross-validation. The other thing that I wanted to show you is random forests, extra trees, and Adaboost. And again, these are all different ensemble techniques that you can use. And this is, again, an example code that I found. But basically, it's very complicated. But what it does is it fits a decision tree for each of the features on the iris dataset, and then builds classification on each of them. And I just wanted to show you the intuition of what each of the algorithms look like. So that's decision tree, random forest, extra trees, and Adaboost. And again, it gives you a probabilistic estimate on where it'll be. I guess what the class is. So hopefully that gives you some intuition of the different algorithms that we learned in class and how to apply them. They're as simple as just importing that. So if you want to use decision trees, it's as simple as just importing the classifier, naming it. You can call it model. Sometimes people call it CLF, and then you can do CLF.fit, and then it'll build your classification based off your X data and your Y data, and it will allow you to do classification right off the box. So it shouldn't be too difficult. The main part is really picking the right algorithm and picking the right parameters. So I showed you a couple of them. In the future tutorials, I'm going to show you a couple more, and then we're going to go over model evaluation and ways to be able to evaluate which is the best model to use. But again, it's very important that you visualize your data and you try and understand what's going on and how the classification is being made, and really figure out if you're underfitting or overfitting based off the results that you get. So for your basically what I would recommend is try using naive Bayes, see what scores you get. Try using decision trees, see what scores you get, and then if you have time, play with the random forest, or try the Bernoulli naive Bayes, or try different examples. And sometimes you can find sample code on the internet. So I guess we are out of time, and that's kind of what I prepared for this tutorial. Hopefully you found that helpful.